Woohoo! Welcome back. Today we're going to be talking about the first part of the applications of differentiation, and that is looking at maximum and minimum values. But before we do that, woohoo! It's time for Latin. Yay! Okay, so in the world of Latin, and Latin forms a lot of the basis of the words we use in math, you should know that there are actually 3 genders. It's very exciting. There's the masculine, the feminine, and there's also something called neuter. And neuter was neither maximum, masculine or feminine. It's something else. And so here we've got things that end in like maximum, and that's singular. So like there's one maximum, but if you want to say plural, there's lots of them. It gets a little bit different. It turns into a, and that's how you make the plural, which is a little confusing because that's also how the feminine form ends. And so people are like, how do you know the difference? And the answer is, well, you do if your mom insisted you take Latin in 7th grade. So there you go. And I'm not bitter, a little bitter. Yeah. Okay. So maximum is singular, maxima is plural. And let's thank my mom because I can explain that to you. It was very important that I take it for 2 whole years to be able to explain that. But let's move on. Woohoo! Local maximum and local minimum is what we're looking at right now. And so what I wanted to do was to look at a graph so that I can try to explain what these concepts are, because honestly, some of the concepts are a little bit confusing. And so let me see if I can get this graph to fit on in a reasonable way. There we go. There we go. Okay. So I've got 4 different concepts here. I've got the concept of a local maximum. Oops. I've got the concept of a local minimum. The concept of an absolute global maximum. And then I also have the concept of an absolute or global minimum. So what the heck is the difference? Because we're using all the words a couple different ways. So a maximum is the biggest, right? And the minimum is the smallest. So max is big. And a min is smallest. Now, there are 2 ways you can be big or small. So let's take a look at this graph. So if I look at the whole graph, and you might need to use a ruler for some of these graphs because it's not obvious, but I stole this one from the book. But if you hold a ruler here, we see that this right here is the biggest value on the whole graph, that point right there. But I'm not going to color it in blue. I'm going to color it in green. It's the absolute, the overall maximum. Okay. Now let's take a look and let's look for the absolute minimum. That one's, I think, a little easier to see. What's the absolute lowest point in terms of y? And we're always looking at y. So max, let me write that in. That's a good point so that I'm very clear. That's the biggest y value, and the minimum is the smallest y value. We're not looking at x, we're looking at y. We're looking at the output. And so our minimum y is going to be down here. Does that make sense? So that's the absolute max and the absolute min. But that's not everything that's happening inside. We've also got something called a local maximum. So now this might be, for example, the richest person in the country. Okay. But then we could also have the richest person in the state. Now, they're not as rich as the richest person in the country, but they're still doing pretty well. And so we're going to talk about them being the local max. Now, if we look in really closely, what's going on? Right in a little neighborhood around them, the state, they look, if you cut out everybody else, they look like the maximum for everything nearby. Do you see how that is? So they're considered a local maximum. They are not the absolute or global maximum. They're just the biggest one in their neighborhood or in their state. Let's look at this point right here. You notice I've got out my yellow highlighter. I claim this is a local minimum. Again, how we do that is we block out everybody who's further away, and we look at just a little neighborhood around it. And we see at a neighborhood around it, it is the smallest point, right? It goes down, and then you get that point, and then it goes back up. So that is called a local min. Are there any other local mins? And the interesting thing is, yeah, there is. The global min is actually a local min, right? Because if we ignore everything else, that's the smallest point. That's the lowest point in that neighborhood. So now you should be asking me, okay, what about these points? These should be global maxima. And the answer is they're not. Because if you block off this, we can see that it's going up to that point, but we don't know what happens after that. It might keep going. It might turn around and come back down. We don't know if it's actually locally the biggest one. We just don't have enough information. So when we get to the edge of a graph and we have the two endpoints, if we've restricted the domain or if the domain just happens to be restricted, if it's an endpoint, you cannot be a local min or a local max. See how that says that? So now, why are we doing any of this? Why does any of this matter? And the answer is, well, there's some things that happen. A local min means that the graph is coming down. It hits this point, that's that local minimum, and then it turns and goes the other way. At a maximum, it's heading up, it hits that point and turns around. Again, at this point, it goes down and turns around. So at all of the local maxima and local minima, or the other word is extrema, is what we call it. At all of these points, the graph turns around. And that would be really great to know. When does the graph turn around? So that's why we're going to be studying it. But it also helps us graph the graph. So that's going to be helpful. Okay, so what is f prime of x at the local extrema? So now you're going to have to fuzz your eyes a little bit and try to figure out what the slope is. So let's look at this first point here when x equals 0. I'm going to try to draw in some tangents. The tangent line comes in like this, comes in like this, comes in like this. It goes around the bottom. And you see how then it turns back around and heads up this way? I claim that right at that point, the tangent line is horizontal. So the slope equals 0. So far, so good? What about this point? Could I convince you that it was also has a tangent line that looks like that, where the slope equals 0? And how about this one? So every time a graph turns around, it has to completely turn around. It has to go from decreasing to increasing or increasing to decreasing. It goes all the way from a negative slope to a positive slope. Where does it have to go through in the middle? If it's negative over here and positive over here, it's got to go through 0. And so the local extrema, that's max and min, the slope equals 0. So that means the first derivative equals 0. Now, what about the absolute extrema? Well, those are the overall global for the whole world. Literally global refers to the world, right? Because it's a globe. You can't say anything. Because sometimes, right at this point, at 3, -27, the slope is 0. But over here at -137, I don't know, what's the slope? I'm gonna have to make it flat. Let's see, this slope kind of comes up like this. It's pretty big. It's negative. It's some negative big number. I don't know what that is. It's definitely falling at that point, but or decreasing. So I'm just going to say, let's run everything into my lamp. And then we're going to say the slope is negative big. I don't know what it is. There is no consistent rule. But with local extrema, because you have to go through the process of decreasing, then increasing, or increasing, then decreasing, you have to go through the slope is 0. Okay, so that's kind of interesting. So let's see what we can do with this. Now what we're going to do here is we're going to look at exactly the same graph. Oh, all my other notes are showing through. The light is too bright. Oh, don't peek, don't peek. Look, pterodactyl. Pterodactyl, look over there, look over there. There's a pterodactyl to your left. Or your right. No, I think it's your left. It's my left. Oh, it moved to the right. Oh, it's moved. Okay. Flap, 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 flap. There it goes. Same exact graph, but I want to look at it on the closed interval from 1 to 3. I'm sorry about the bumping on the table. So I want to look from here, where we've got the point 1,5, to here, and I've got the point 3, -27. So I only want to consider this area right here, okay? We're just going to look at that interval. Identify the following. On this graph, and let's see, let me get the colors the same. There was local max is going to be blue. Local min is going to be yellow. Absolute/global max is going to be green. And absolute min is going to be purple. Okay. So, in this, from x equals 1 to x equals 3, are there any local maxima or minima? Are there any local extrema? And remember that a local max has to be something that looks like this, and a local min needs to look like something like this. So it's got to be a little ant standing on top of a hill or an ant sitting in the middle of a valley. And the answer is, we've got part of a hill here, but since we're crossing off the rest of it, we don't get to count it. It's an end point. Same thing here. It looks like the bottom of a valley, but since that's the end of that interval, it's an end point, so it doesn't count. So believe it or not, there are none. No local extrema, which is weird because, as we're sitting here in a godlike position, we can see that this is absolutely a local max and this is absolutely a local min. But when we restrict the domain, we look just at this interval, we don't get to count them because they're endpoints. And we officially don't know what happens outside of that interval. Okay. Is there an absolute max? Yes. On a closed interval, there will be a biggest value. Now, will there be only one of them? Not necessarily. You could have a horizontal line. So the absolute max could be the same for all the points. So do we have an absolute max? Yes. Absolute or global max is not restricted at all. And unfortunately, we don't use it a lot because it's a lot easier to find. It'd be great if we use it a lot, but we don't really. And so here I've got the absolute minimum and the absolute maximum. Ta-da! So, what is f prime of x at the local extrema? There are none, so we can't answer that question. What is f prime of x at the absolute extrema? Here, it's a little bit complicated because it's closed, so we can actually look at these 2 points and we can say, okay, the slope is coming in, and it is, because we can see the larger picture, and so without having to take the derivative, right, we can actually visually do it. We could actually, well, why not? Why don't we? Why don't we? So if f of x is 3x to the fourth minus 16x cubed plus 18x squared, the first derivative is going to be 12x cubed minus 48x squared plus 36x. I really regret this already because you can't see my work either. Sorry, I keep running into my lamp. So there we go. The derivative, take a look at that. Make sure that I did it. I did it off in secret where you couldn't see it, but make sure you double check. Did I get it? I hope I got it. We're going to find out. What happens when x is 1? I get 12 times 1 cubed minus 48 times 1 squared plus 36 times 1, and that equals 12 minus 48 plus 36, which equals 0. So it turns out at this absolute max, we do have the slope equaling 0. And what about at the absolute minimum? When we plug in 3, so do we really want to do this? Yeah? Okay. 12 times 3 cubed minus 48 times 3 squared plus 36 times 3. I don't have my calculator on me. So this is 12 times 27 minus 48 times 9 plus 36 times 3. So that's going to be 270 plus 54 is 324 minus 9 times 8 is 9 times 9 is 81. 9 times 8 is 72. 2 carry the 7. 9 times 4 is 36 plus 7 is 43. And then we're going to subtract 36 times 3, which is 72 plus 36, which is 108. And that, in fact, also equals 0. There we go. Woohoo! So the derivative at each of these are 0. But is it because they were absolute extrema? And the answer is no. It's actually because they're local max and local min. And so, because what could happen? Well, what if on the graph I had shut it down at 1.5? Then the local max would be here at 1.5, and that's the slope is just going to be -1 or something like that. Same thing here. If instead of going all the way to 3, I'd gone to 2.5, our global min would be right there, and the slope wouldn't necessarily be 0. So what's happening here? Well, what's happening is every time we have a local min or a local max, we've got that slope equal to 0. And so we can look for that. When we look for absolute extrema, is the slope always equal to 0? Well, no, because on the first page, we found out, sorry, you can't see where my fingers are. We found out that the slope was actually not equal to 0 at one of the points. So you can't know that for sure, unfortunately. Okay, you guys ready? Dun, dun, dun. Math. Okay. The extreme value theorem. This is a really big one. If f is continuous, remember continuous, on a closed interval, it has to be closed, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d and a, b. So in other words, if you have a closed interval, there will be a biggest y value and a smallest y value. That's all that says. You're guaranteed one. Now, is it possible that there will be many points? Sure. So, like, for example, I could have something as simple as this. This would be a global min, and this would be a global max, right? And I just figure out what those values are. This y value, whatever y value it is, this is the global max and the global min. And it is the same y value, and it is true for all x. So you can have a lot of different situations. You could also have something where you could have, like when we've looked at trigonometry, you could have a bunch of global max and global mins, or I should say points where the global max and the global min occur. The actual value is whatever the y value is. So whatever the y value is, so if this is like the point 4, 5, and this is the point 1, 2, then the global max here would be 5. The global min here would be 2. Does that make sense? Here, this is just y equals 3. The global max is 3. The global min is 3. Does that make sense? So it's whatever the value is. Okay. Why does the interval need to be closed? Well, we have to avoid asymptotes. If I allow it to be an open interval, then I'm allowing for something that looks like this. And then does this ever achieve a maximum value? And the answer is no. It just keeps going up and up and up forever. So it has to actually be closed. You have to have f of a and f of b being existing values. Does that make sense? We want f of a and f of b to exist. So that's why we say it's closed. We can't do any of these. Well, it just gets bigger and bigger and bigger, and it never quite reaches. We're not going to include that because that's going to be a different situation. Okay, so that's an exciting one. And we're going to drop it like a hot potato, because then we're going to get Fermat. And I know it looks like Fermat, but you say the T gets unspoken. So it's like Fermat. Very fancy. If f has a local max or a local min at C, and f prime of C exists, then f prime of C will be 0. So if you have a local max or a local min, the derivative will be 0 if it exists. Now, why don't we do it the other way around? It'd be so much easier if we said, if the slope is 0, then we get a local max or min. And the answer is, it's not true. So when I say, note that this theorem is limited, it only goes in one direction. So in other words, if it's a local max or min, then the derivative, oops, oh no, where's my, there we go. Then the derivative is 0. This does not go back the other way. You can't start at 0 and then guarantee yourself a local max or min. So if there is a local max or min, then the derivative is 0, or f prime of C doesn't exist. So DNE does not exist. Okay, so what the heck does this look like? Well, let's look at it. It means that if we find all the places where the first derivative is 0, then we will have a complete list of possible local extrema. which tells us then where the graph turns around, where it goes up and comes back down, or where it comes down and comes back up. So that's how we're going to use this. So we're going to start off with a graph you guys already know. F of x equals x squared. And we're going to figure out where the first derivative is 0. So if f of x equals x squared, then what's f prime of x? You got it. It's 2x. Woohoo! Yay! Okay, so then we look for when f prime of x, which is 2x, when is that equal to 0? Well, when is 2x equal to 0? Oh, it's just when x equals 0. Okay. So what does that mean? There might be a local max or min at x equals 0. And what else? And there aren't any other possible spots. So what this is telling us is there's either a little bump up or a little bump down, and there's only one of them at most. Now, we happen to know what x squared looks like, right? X squared is a graph, is a parabola. Is there a local max or a local min? Yes, there is. It's right there. So yay! This is a local min at x equals 0. Now, you should be asking me, how do we know that? And the answer is, well, I picked a function that you know how to graph. So either you graph it and look at it, or you do some stuff later on. Mysterious things. Ooh. So for right now, pretty much we're going to graph it and look at it, or we're going to look at other values near it. Like we could look at what happens between x equals 0 and x equals 1 or x equals 2, and we could, kind of plot points to figure out. So right now we're kind of very theoretical and a little bit unsatisfying, unfortunately. So let's try some other unsatisfying examples. Yay, let's hear for unsatisfying examples. Woohoo! Okay, just 2 more examples, and then I'm going to cut this video, and we're going to do another video. We'll have one more big example, but that'll be in the next video because it's getting kind of long in the tooth. Feel free to pause the video anytime you want, because seriously, this is a lot, and this is very theoretical. Uh-oh. That's no good. There we go. Tried to make it bigger, and I just made it disappear. But go ahead and pause these videos anytime you want. 20 minutes is supposed to be the longest you're supposed to actually stare at a screen. I'm not staring at a screen technically, but I am staring at a very bright light. So I will also take a break after I make this video and, go look at something green or, touch grass, go play, run, frolic, scream, sing, all that stuff, fun stuff, do some art. Maybe play video games, but stay a little bit further away from the screen, right? Change your focal distance so that you can rest your eyes a little bit. Okay, so very similar to x squared, we're going to go with f of x equals x cubed. Okay, I want to find the first derivative. That's 3x squared. And I want to set that equal to 0. Well, same thing's going to happen. 3x squared, I've got basically that x squared equals 0. So that means that x has got to equal 0, right? So then the next question is, okay, there might be one possible local max or min. And so for this, we're going to take a look at the graph. And when I look at the graph of x cubed, what do I get? You guys remember? Hopefully it's one of the ones, I picked these because I thought they were the ones that we generally talk about as being the important ones to kind of have a sense of them from just knowing. But the graph looks like that. What is happening at x equals 0? Is that a local max or a local min? And the answer is, well, why is the slope 0? Well, the slope is 0 there because if we look at the tangent line and we start drawing it, we look at this tangent, we see that it kind of, and this is my poor graph, doesn't draw it very well, but it comes from very positive, it kind of flattens out in the middle, and then it goes back up to being positive. Notice that it gets ready to turn around like a parabola, but instead of turning around and going the other direction, it keeps going. And so this is neither a local max or a min. And this is really unsatisfying. So now I need to give you a phrase. X equals 0 is a critical value. I think the book calls it a critical number. I'm trying to remember what the book calls it. I call it a critical value, and basically that means that you look for all the derivatives, you find the derivative, you set it equal to 0, you find all the points where the first derivative equals 0, and then that's a critical value. And that means that, yes, the slope is in fact, oh, that's a terrible drawing, but take my word for it. That means m equals 0. The slope is 0 there, but it's neither a max nor a min, but it's the possibility. And then the next question is, are there any points, other points in the whole graph where it could possibly be 0? And the answer is no, it just happens here. So then what we know is when we draw this, we know it just keeps going up. We know it doesn't suddenly turn around, because if it turned around, what would happen? You'd have a local max. Or if it goes down and then turns back around, comes up, you'd have a local min. And so this is how we're going to use these critical values. These critical values are going to tell us where interesting things happen. Is it always a local max or a min? No. Sometimes it's just kind of a little flattening out, and then it's taking a little rest. It's done a lot of work. It's like, okay, I'm going to rest. Okay, now we boom, and then we back up into the stratosphere. Okay. Dun, dun, dun. You guys ready? One more example, and then the video's done. Oh my goodness. Dun, dun, dun. Now, why am I dun, dun, dunning? Well, personally, do I have an issue with absolute value? I do. Absolutely. If I didn't have dad jokes, I wouldn't have any jokes at all. Okay. So you got to remember what the graph looks like. And the graph is really interesting. The graph looks like y equals x on the right, and it looks like y equals the opposite of x on the left. It's a 45-degree angle in each case. And it's kind of interesting. Absolute value, right? It basically says if x is positive, y is just whatever x is. And if x is negative, y is the opposite of x. So it makes it kind of come in and reflect. It's like light hitting a surface, a perfectly reflective surface. So what is the slope over here? If this part of it, and let me write out, if you don't recall, absolute value of x is actually defined as a piecewise defined function. It's x for x is greater than or equal to 0, and it's the opposite of x for x is less than 0. So if this portion right here, so let's call this the blue piece, because I grabbed blue first. This is the blue piece. So in this portion, f of x equals x, so f prime of x is 1. So that's the slope. The slope is 1. Does that make sense? Okay. Now let's come over here to the other side. When x is negative, f of x is, oops, you can't see that. the opposite of x. So f prime of x is -1. So over here, the slope is -1. So you've got, on this side, the slope is 1. And on this side, the slope is -1. And I don't know if you remember it, but right in the very beginning of derivatives, when we started looking at what derivatives were, we said it had to be continuous and it couldn't be a corner or a peak, like a pointy bit, or one of those curves like half dome that suddenly stops. You can't have extreme corners. And there's a corner right here. And because these two slopes, I mean, they just don't agree. One is 1 and one is -1. So what is the slope right there when x equals 0? The slope is undefined. Although a lot of people say, well, it would make sense if it were 0. And I've always thought it should be 0, but we don't include corners because there's such a just sudden switch from slope equals 1, slope equals -1, and then just completely different values. So this is interesting, though, because there is a local min at x equals 0. And if we go back to Fermat, which we kind of rushed through the first time, it says if f has a local maximum or minimum at c, and if the derivative exists, then the derivative is 0. And that only goes in the one direction. But one of our possibilities is the derivative doesn't exist. This is a case where the derivative is undefined, and there's a local minimum at x equals 0. So now what we have to remember is either we take the derivative and find where the derivative equals 0, easy peasy, or we look for where the derivative is undefined. So two cases we got to look for: equal to 0 and undefined. And honestly, at this point, we're in almost 38 minutes. If you guys are still watching, I'm very, very impressed. I know in class you guys said longer videos are good, but this one's pretty long. So definitely go take a break. Give yourselves a big hug for making it through. Woohoo, you guys are awesome. This was very theoretical. The very next video I'm going to make is a really nice example that'll show you, like, what do we do? How do we actually use all of this stuff that we've been doing? How do we use it to actually solve some problems? So that's the next one. It should be a nice, quick and dirty. It's a beautiful little polynomial. You'll love it. And until then, though, I'm going to say, take care of yourselves. Take a break. Go pet an animal, or go hang out with friends, or go say hi to your family. Remind them who you are. And maybe make some food, or go dance, or do some art, or do more math, do your homework, or whatever you'd like to do. Take that break and then come back. And until then, woohoo, because you guys are awesome, and math on.